Artificial intelligence. Intelligence of machines or software. AI, redirects here. For other uses, see AI, disambiguation, artificial intelligence disambiguation, and intelligent agent. Artificial intelligence (AI) is the intelligence of machines or software, as opposed to the intelligence of living beings, primarily of humans. It is a field of study in computer science that develops and studies intelligent machines. Such machines may be called AIs. AI technology is widely used throughout industry, government, and science. Some high-profile applications are advanced web search engines, e.g., Google search recommendation systems used by YouTube, Amazon, and Netflix, interacting via human speech, e.g., Google Assistant, Siri, and Alexa, self-driving cars, e.g., Waymo, generative and creative tools, e.g., ChatGPT, and AI art and superhuman play and analysis in strategy games, e.g., chess and Go. Alan Turing was the first person to conduct substantial research in the field that he called machine intelligence. Artificial intelligence was founded as an academic discipline in 1956. The field went through multiple cycles of optimism, followed by periods of disappointment and loss of funding, known as AI winter. Funding and interest vastly increased after 2012 when deep learning surpassed all previous AI techniques, and after 2017 with the transformer architecture. This led to the AI spring of the early 2020s, with companies, universities, and laboratories overwhelmingly based in the United States pioneering significant advances in artificial intelligence. The growing use of artificial intelligence in the 21st century is influencing a societal and economic shift towards increased automation, data-driven decision-making, and the integration of AI systems into various economic sectors and areas of life, impacting job markets, healthcare, government, industry, and education. This raises questions about the ethical implications and risks of AI, prompting discussions about regulatory policies to ensure the safety and benefits of the technology. The various subfields of AI research are centered around particular goals and the use of particular tools. The traditional goals of AI research include reasoning, knowledge representation, planning, learning, natural language processing, perception, and support for robotics. General intelligence, the ability to complete any task performable by a human, is among the field's long-term goals. To solve these problems, AI researchers have adapted and integrated a wide range of problem-solving techniques, including search and mathematical optimization, formal logic, artificial neural networks, and methods based on statistics, operations research, and economics. AI also draws upon psychology, linguistics, philosophy, neuroscience, and other fields. Goals. The general problem of simulating or creating intelligence has been broken into sub-problems. These consist of particular traits or capabilities that researchers expect an intelligent system to display. The traits described below have received the most attention and cover the scope of AI research. Reasoning, problem solving. Early researchers developed algorithms that imitated step-by-step reasoning that humans use when they solve puzzles or make logical deductions. By the late 1980s and 1990s, methods were developed for dealing with uncertain or incomplete information, employing concepts from probability and economics. Many of these algorithms are insufficient for solving large reasoning problems because they experience a combinatorial explosion. They became exponentially slower as the problems grew larger. Even humans rarely use the step-by-step deduction that early AI research could model. They solve most of their problems using fast, intuitive judgments. Accurate and efficient reasoning is an unsolved problem. Knowledge representation. An ontology represents knowledge as a set of concepts within a domain and the relationships between those concepts. Knowledge representation and knowledge engineering allow AI programs to answer questions intelligently and make deductions about real-world facts. Formal knowledge representations are used in content-based indexing and retrieval, scene interpretation, clinical decision support, knowledge discovery, mining, interesting, and actionable inferences from large databases, and other areas. A knowledge base is a body of knowledge represented in a form that can be used by a program. An ontology is the set of objects, relations, concepts, and properties used by a particular domain of knowledge. Knowledge bases need to represent things such as objects, properties, categories, and relations between objects, situations, events, states and time, causes and effects, knowledge about knowledge, what we know about what other people know, default reasoning, things that humans assume are true until they are told differently and will remain true even when other facts are changing, and many other aspects and domains of knowledge. Among the most difficult problems in knowledge representation are the breadth of common sense knowledge, the set of atomic facts that the average person knows is enormous, and the sub-symbolic form of most common sense knowledge. Much of what people know is not represented as facts or statements that they could express verbally. There is also the difficulty of knowledge acquisition, the problem of obtaining knowledge for AI applications. Planning and decision making. An agent is anything that perceives and takes actions in the world. A rational agent has goals or preferences and takes actions to make them happen. In automated planning, the agent has a specific goal. In automated decision-making, the agent has preferences. There are some situations it would prefer to be in, and some situations it is trying to avoid. The decision-making agent assigns a number to each situation called the utility that measures how much the agent prefers it. For each possible action, it can calculate the expected utility, the utility of all possible outcomes of the action, weighted by the probability that the outcome will occur. It can then choose the action with the maximum expected utility. In classical planning, the agent knows exactly what the effect of any action will be. In most real-world problems, however, the agent may not be certain about the situation they are in. It is unknown or unobservable, and it may not know for certain what will happen after each possible action. It is not deterministic. It must choose an action by making a probabilistic guess and then reassess the situation to see if the action worked. In some problems, the agent's preferences may be uncertain, especially if there are other agents or humans involved. These can be learned, e.g., with inverse reinforcement learning, or the agent can seek information to improve its preferences.